Hi, welcome to the fourth week of lectures. Before I begin, let me try to revise what we have seen so far. So far, we have been trying to formulate a notion of information, a mathematical formulation of information, and we are going by the central thesis put forward by Shannon. He said information is reduction in uncertainty. All right, and we have been trying to mathematically formulate this principle. Well, how do we use something like this mathematically? Well, first we'll have to find mathematical measures of uncertainty. And we did this by defining two different notions of uncertainty. For the first one we were looking at is little to compression. It is defined as the minimum number of bits required to store a random variable or to represent a random variable. Okay, this can be thought of as a measure of uncertainty in the random variable. Now there are various ways to formulate this problem. We saw two particular ways. One was we wanted to formulate what is the minimum fixed number of bits required that will allow us to recover the random variable correctly with large probability. That was one kind of notion. Another kind of notion can be what is the average number of bits required, which will allow us to recover the random variable exactly. Okay, we saw these two different notions, and it turned out that the answer to both these notions was this quantity, which was called Shannon entropy. Right, and we denoted this by h of p, and we gave a very nice formula for this. This is a very important formula for this course. It is simply px log, about this, px log 1 over px. Okay, so this is Shannon entropy that we saw. So this is our first, this is a notion of a measure of uncertainty, which came out as an answer to this first question. Then in the previous week, we saw another question. We saw that maybe we should measure uncertainty differently. We wanted to measure uncertainty as the amount of randomness in a random variable. And there are two ways we thought about this problem. One is how many uniform random bits are needed to generate a random variable. And the second form was how many uniform random bits can be extracted out of a random variable. These are two different ways to formulate the question about the amount of randomness in a random variable. And it turned out that the answer to both these different questions was also the same, namely the Shannon entropy. Therefore, the Shannon entropy comes out as an answer to measure of randomness or measure of uncertainty in a random variable in more than one ways. And it is a fundamental quantity which will come out again and again in this course. So from here on, whenever we think of what is the measure of randomness in the random variable, we can simply just take Shannon entropy as the answer to that problem. So coming back to information revealed when you get to know an unknown x. So suppose you had this guess for a random variable, which you have a guess for something like temperature in the city, and that's some guess that you have in your mind. How would you have this guess? Well, most likely you have a probability distribution which you have formed. Okay, and that's your random variable. And now I reveal this random variable to you. I told you about this random variable. So for instance, perhaps you have some probability distribution on who will win the election. Let's say the upcoming election in Bihar, who will win that? Suppose you have a probability distribution which describes that. And when you will see the outcome of the election, how much information will be revealed? So there is a mathematical way to do that. So here is the mathematical way to do that. Uncertainty before the answer is revealed is h of x. And once you know the answer, there is no uncertainty, so this is 0. So how much does the uncertainty change? Well, it changes by h of x. So the day you will see the result of the election, the information revealed to you will be h of x, the entropy of the random variable x. Okay, so this question is roughly we have some handle over this question, but perhaps it doesn't answer a more natural question. We are often interested not in understanding how much information about x is revealed when you see x, but we are interested in understanding how much information about x is revealed by some other random variable y. So how much information is revealed about x when y is revealed to you, when y is given to you. And this is the question we'll examine in the next 2 weeks. And to answer this question, we will actually formulate a problem in statistical inference. Okay, so you can treat this these next two lectures as a very quick introduction to basic statistics and their connection and its connection with information theory. All right, so we will see some other ways of handling of defining information, and once again we'll see that measures related to entropy come out as an answer to this question. All right, so see you in the next video.